Hello, I'm Juan de la Aguila Ferrandis from the University of Edinburgh, and I will be presenting our recent work on non-prehensile planar manipulation through reinforcement learning with multimodal categorical exploration. We consider the task of pushing a box to an arbitrary target pose from an arbitrary initial configuration. We aim to use model-free RL to learn this task. We're given an observation of the current box pose and the current pusher position, as well as a target box pose. The policy predicts the x and y velocity of the pusher required to move the box towards the target. Previous works applying RL to planar pushing have used Gaussian exploration. This results in unimodal policies that achieve low accuracy, non-smooth trajectories, and only simple motions, disregarding the orientation of the manipulated object. In particular, they have been unable to learn the planar pushing task with arbitrary initial and target poses. Motivated by previous model-based works, which identify planar pushing as a hybrid dynamic system with a set of different contact modes, such as sticking, sliding, and separation, that constrain the control actions, we hypothesize that we can reason about planar pushing as a multimodal control problem. Therefore, we proposed a multimodal exploration approach through categorical distributions on a discrete action space, potentially leading to more effective exploration of different contact modes. Our policies are trained entirely in simulation using PyBullet. We abstract away the robot during training and only consider a spherical pusher in order to reduce training time. We deploy 128 parallel actors to collect data and update the policy. Additionally, to bridge the sim-to-real gap, we use dynamics randomization, observation noise, and synthetic disturbances. An episode is considered successful if the box position and orientation are within certain thresholds of the target. We define a curriculum such that the training starts with larger thresholds. Then, if the policy exceeds a 90% success rate, we have the success thresholds. We evaluate PPO with Gaussian and categorical exploration, as well as MLP and LSTM architectures for the policy and value functions. We also evaluate SAC with Gaussian exploration as a baseline for comparison with previous work. We find that only the policies using the proposed categorical exploration approach manage to learn the task. We also verify that indeed during training, when using the proposed categorical exploration approach, the action distributions often exhibit multimodal exploration strategies. Additionally, we examine the performance of the policies with Gaussian exploration on a simplified planar pushing task, where the box starts on the left, the target is on the right, and the starting and target orientations are constrained within a range of pi-half radians. We remove the synthetic disturbances and make the pusher start at the backside of the box, the natural pushing phase in this scenario. A curriculum progressively increases the range of starting and target orientations. We find that the policies fail to make significant progress with the curriculum. We believe this is because they struggle with the tasks that require phase switching due to the Gaussian exploration being unable to effectively capture this additional modality. We also show that our framework can be easily scaled to a planar pushing task with two pushers. Finally, we validate our framework on a physical planar pushing robot setup. The robot is able to seamlessly switch between different contact modes and recover from large external disturbances. It achieves smooth trajectories and manages to successfully reorient the box, even in cases with a large angular distance to the target orientation. Overall, the robot consistently solves the planar pushing task given arbitrary initial and target box poses with significant accuracy. Thank you for your attention.